Thank you, Vignesh, for the introduction. And essentially, what I would like to talk about today is, in many ways, my career graph. And in a way, I would like to inspire more students to take up a similar path. So, as Vignesh mentioned, after my graduating from IIT Calicut in the mechanical engineering department in 2009, I went on to do my doctoral studies, then on to a few years of postdoc work at Argonne, after which I decided to move to Germany. Now, before I start with the talk, I would like to give a quick background about my research, but that is primarily because I think that provides context to the rest of the talk and where my opinion about the career in computational sciences comes from. So currently, if I'm supposed to give an elevator description of what I do, I'm a mechanical engineer in the pharmaceutical industry. So it all started with doing some nanoscale heat transfer work with Shobhan sir at NIT Calicut. The skills gained from there helped me go on to my doctoral studies. And from there on, I've worked on several projects, used several tools, such that there was sufficient overlap between my skill set and what was needed in the pharmaceutical industry, that eventually I started working at Avantgarde Material Simulation. And a special mention in that regard would go to the work I did at Argonne. When you look at this slide, initially it looks like there's absolutely nothing to do with pharma industry. There are lots of inorganic crystals. There are nanocrystals. You're looking at heat transport. But all those underlying tools that are used here are like molecular dynamics, force field parameterization, free energy calculations. All of this are necessary skill sets that are transferable to many industry domains, including the pharma industry where I currently work. So with that, essentially this talk is going to cover what computational science is. I'll go over some introduction into different fundamental theories and simulation methods, following which I will move into something more application-oriented, which would be an application-driven predictive multiscale simulation, which may or may not be commercially viable, but the ultimate holy grail get application-driven integrated multiscale simulation. That will naturally lead on to what the role of a computer scientist is in the industry. A brief discussion on whether after you finish your graduate studies, or whether you do a PhD or not, whether you want to continue in academia or industry, what kind of industry opportunities are out there, and how one can plan a career as a computational scientist. So some of the key take-home messages I would like to convey by the end of this talk. I put this up at the beginning so that personally I and all the listeners can evaluate whether these key points came across through the talk or not. One is to convey that computational sciences is of industry relevant and will become more so in the future. And there's a special importance for having specialized computational workflows for commercial viability. I hope some skills needed for seamless cross-transition between academia and industry will come across. I'll briefly talk about some types of job opportunities that students who pursue this career path can have. And also, hopefully I can get a few points across regarding what mistakes and pitfalls have to be avoided. So I'll start with what computational science is. So let's take a look at this Venn diagram. Let's start with what I consider the most important part is, and that's the fundamental science domain knowledge. Now, I list here a few examples of what I mean by fundamental science domain knowledge. Of course, you need not be an expert in all of them, but a few of them would be important to essentially have to be a computational scientist. For instance, there's quantum mechanics if you are a computational chemist. Likewise, thermodynamics and kinetics, which cuts across different branches of computational sciences. If you're a computational physicist or a mechanical engineer who graduates into computational science, you will also need mechanics and fluid dynamics. But apart from that fundamental science knowledge, someone who works in computational science, whether in academia or the industry, would also be dabbling a lot with computer science. There'll be a lot of programming involved, knowledge of parallel computing, setting up IT infrastructure to run calculations on HPC and the cloud. There is also lots of applied math and numerical methods such as local and global optimization, automatic differentiation, probability theory, linear algebra, etc. And those three circles, or the intersection of those three circles, is what is traditionally referred to as computational science. But of late, with machine learning becoming more prominent, there is this fourth branch, which is also relevant to what the computational scientists do. I'm calling it slightly different. I'm calling it data-driven computational science. So while all of these areas are important domains that a computational scientist should know, the most important one that I consider is the fundamental science domain knowledge. So to have a seamless cross transition between academia and industry, one needs to have a breadth of knowledge across all these domains with sufficient depth in each of these. And in my opinion, the most depth has to be in the fundamental science domain knowledge, and the tools that are used to extract fundamental theory is what I'll be initially focusing on in this talk. So in terms of different fundamental theory or fundamental simulation methods, we can start with what at the atomistic level, where you explicitly treat the atoms. Now, of course, when you start treating all the atoms, there are so many interactions to consider that simulations are expensive. So for all practical cases, so a density functional theory, which is the closest approximation we have currently to solving actual Schrodinger's equation, we are restricted to systems of about nanometers in size, simulating timescales of a few tens of picoseconds. If you start using still atomistic but more empirical methods such as molecular dynamics, you can go further out up to micrometers in size and even up to milliseconds in timescales. And these techniques are basically used to look at atomistic phenomena, evaluate certain properties like when an electron is excited in an atom, how do we physically see that response? How do we see that response in nature? Evaluating properties of surfaces, looking at actual reactions that happen on catalysts. But we can move further into the next domain, which would be what is called mesoscale. Here we have coarse-grained molecular dynamics simulations, certain empirical theories for phase field models, which and in the mesoscale, you're essentially able to simulate up to millimeter length scales, and even go up to seconds in time scales. But reality is which is at the macroscopic scale, is mostly described by the continuum methods, such as computational fluid dynamics or finite element methods. Now, of course, when you start creating advanced problems, inputs to these models, whether it's a CFT model or an FEM model, are unknown. So if you do not know what material properties to choose, for a particular component in your model, you would not be able to actually get anything meaningful out of a continuum simulation. And so essentially the goal is to build down from the top, find an application, describe it with its closest continuum model for all missing properties, go down deeper and deeper into additional levels of theory to extract all the information that you do not have to describe reality. So essentially what I mentioned here is what I would call an integrated multiscale simulation, where you start from the top, find the closest description to reality in a continuum model, and for all missing information, you go deeper and deeper at the fundamental level to get that information out. And let's just start small, look at some academic research I've done as part of Argonne and other research to integrate different simulation modalities and to mimic experiments. So that's what I'll be starting with. But before I get there, let's take a look at what I have on the slide, which is, let's start with fundamental theory. Fundamental theory is a mathematical framework of nature, and that would be a highly microscopic look at what we actually see in nature. So let's take an example as one bubble in a bubble wrap. A simulation, or when you do computational experiments to investigate origin of properties, you zoom out a bit and you start seeing a little more of a detail. But as a computational scientist, if you stop there, which unfortunately happens quite a lot in academia, there is a risk of losing sight of the forest for the trees, which is a bigger picture application where you have a pattern, let's say a pattern that appears which is not visible if you zoom in and stay in a silo of only looking at the fundamental theory. And an industry career is fundamentally about looking at this big picture application. And one of the holy grails, and which there are lots of companies that have started working on this, is to design an application with real-time feedback from fundamental theory that governs the smallest unit relevant to the application. That, in other words, is very similar to what I said before. Find a continuum model that describes reality, and for every missing information, go deeper and deeper till you get all the fundamental information that you need to model reality. And that is ultimately the goal of having an integrated multiscale simulation. And with that, I'll go into some of the research I've done in the past. But this only looks at some of the smallest portions where we try to integrate some of the simulation components and comparing with experiments. And here, this work was mainly done as part of a 3-year project at Argonne. It was called Modeling, Analysis, and Ultrafast Imaging. Essentially, this work involved plenty of division. It was a highly cross-division collaborative effort. And the ultimate goal was to integrate what I write there as a coherent diffractive imaging with simulation to gain some new insight. In simple terms, Argonne had 2 facilities which they spent a lot of money on. One was an X-ray synchrotron source, one was a supercomputer. The goal of this project was to combine the two to leverage the capabilities of both and to get new fundamental insight. And in this context, there were several projects that we worked on. One of it was essentially on piezoelectric energy harvesters. As I mentioned before, as far as industry is concerned, it's a big picture application that matters. So all of these projects, at least from my end, started with asking what the big picture question was. Here, one of the big picture questions was, you have a material zinc oxide which is used in piezoelectric energy harvesters. Which mode of vibration should be targeted if you want to get to design a piezoelectric harvester with maximum efficiency? And in terms of the work, this essentially started with collecting diffraction data at the synchrotron source in situ, that is essentially while heating a single nano pillar of zinc oxide with laser. And then from the diffraction data, you can essentially do what we call a phase retrieval to get a complete 3D description of the internal strain in the system. And this we extract into a finite element model. So this is the actual nanocrystal that you actually heat with a laser. You couple with an electro-thermomechanical finite element model, and we try to describe what is actually happening in the experiment with this model. And we do a lot of validation studies, but at the end of the day, what we learned from this was a simple answer to this ultimate question: which vibrational mode should be targeted? And the answer here was the torsional modes. Similarly, there are other projects across application domains. So like how this is for energy harvesting, there were also projects on nanocatalysis, where apart from just integrating coherent diffractive imaging with finite element modeling, we also add a layer of molecular dynamics, where there are some missing properties that you get in the nanocatalyst, which comes from an even deeper level of theory. And ultimately, combining all the simulation models, which starts from DFT, molecular dynamics, into a finite element model, we can directly compare with what we actually see in the experiment. However, this alone, as I said, it's starting small. All it does at this stage is it integrates different simulation models and compares with experiments. It's not yet a truly application-driven, predictive multiscale simulation. To get there, what we essentially need is to understand what the industry expectations are. So let's start with, there are two conflicting interests from a scientist point of view and from the top management in a business. A scientist might be excited about a new paper that came out. In this example here is to predict sublimation enthalpy of an organic molecule. A scientist is excited about that, wants to work on it. But as far as someone who runs the company is concerned, what's important is how does that information, how does that new technique help in their drug development pipeline, assuming it's a pharma company. So bridging that difference in enthusiasm or level of enthusiasm that a scientist has and a top management has, one for fundamental level theory, the other for how it impacts their customers. That bridging that gap is essentially what a computational workflow should do. And such a commercially viable modeling tool will essentially support a pipeline of calculations. It should enable or simplify decision making. It should have proper uncertainty quantification, and it should be at a reasonable cost. So a phrase I like to use is a tool that does a series of calculations to predict one key answer that the industry expects is of no use unless you have unless it provides acceptable accuracy at a reasonable cost. And of course, the goal here is to simplify decision making, and the simpler the answer that you can provide, even if the entire tool is complicated, the final answer it provides is simpler, the more the commercial viability. And of course, the predicted data should be robust and reliable with few false positives and negatives. And being able to do that from a computational science point of view is far from trivial. So I'll give one example of where we have an integrated workflow. This is what I do at the company I currently work with, Vanguard Material Simulation. And the workflow is essentially called virtual polymorph screening. We are a small team. We have now, this is slightly old photo, we have 2 more people that we have hired. And we are still looking to hire. So in case someone listens to the entire talk, finds something that is of interest, there are open applications that you can send us. So first, in terms of virtual polymer screening, what is the commercial need? So let's start with something very simple. We have a methanol molecule here. This is a very simple organic molecule, but drug molecules that pharma companies work on will be much larger, much more complicated. But this is a good example to start with. In 3-dimensional space, these molecules can pack in many solid forms. So what you see in the middle here are essentially different ways in which the small molecule can pack in space. And depending on how they pack in space, they will have different thermodynamic stabilities. And if the pharma companies follows a synthesis route and say they crystallize one of the forms, it's important for them to know whether the form that they're going to market is actually thermodynamically stable or not. The reason they need to know that in the commercial need, and the commercial need for this entire tool, is that in case they choose to market the wrong form, and in the future, a more stable form appears after going into production, then the company faces recalls and huge losses. So the companies typically do what's called an experimental polymer screen. So a virtual polymer screen is what our company offers, is essentially a counterpart to the experimental screening, which can provide more information and at a competing cost. So essentially what we do, and why this is an integrated workflow, is we start from just a molecule, such as, this is a typical pharma molecule, which is called rotigotine. We put that into a multiscale workflow, which in our case, it's called GRACE, which essentially combines lots of techniques like empirical force fields, density functional theory, Monte Carlo techniques, pre-energy calculations, some machine learning, to get one simple answer. The chart on the right that you see is the one simple answer we provide to the customers. And apart from that, this has to be integrated with experimental data, so that once the customer collects an experimental data, you place that on that simple answer to truly evaluate whether the form that they're going to market is actually stable or not. So in terms of free energy, the lower it is, the more stable it is. So in this particular example I've shown here, whatever the customer chooses to market the form X is actually at the bottom of the landscape, which means they can go ahead marketing this particular solid form of rotigotine without worrying about whether a more stable form will appear in the future. So this is an example of an integrated workflow which combines experiments, different simulation modalities, and provides one simple answer that decision makers at companies can use to essentially guide their production planning. But this can be enhanced even more. And that's where I come into what the future possibilities are, which will go into what the role of a computational scientist is in the industry, which will naturally lead into how important it is as a student or as someone who works in this field to be able to have sufficient domain knowledge to cross over between academia and industry. So in terms of future commercial opportunities, such a integrated workflow essentially cuts across material systems, applications, and industry, which is mostly facilitated by increased investments in high performance computing and cloud computing as well as machine learning. And in terms of future commercial opportunities, I think there are two main branches two main areas that computational science can branch out into. One would be what is called data-driven models, which would be used for property prediction. So there are some companies who rely on data-driven models. Another would be a physics-based approach, which like what our company does, to have a physics-based approach to have a direct application level prediction. Now, there are many areas, both academic and industry level, that this can apply, such as the space industry, where you can design certain thermal protection materials for rocket nose cones based on such as integrated workflow. The drug API, should that be chosen or not, is something I talked about in context of what our company does. You can also have such integrated workflows to have nanoparticle-based hypothermia to treat cancer cells for a specified target. And as I mentioned earlier, the scope of a computational scientist extends across different industries. There's defense aerospace, where there's nose cone of re-entry vehicles. There's biomedical for cancer treatment. There's pharmaceutical. There's energy. Now, everything listed here are not hypotheticals or wish lists. The first one was worked in part by a company that I worked after graduating. Essentially, this was funded by the Small Business Innovation Grant in the US. Second one is an extension of my PhD thesis. The third on the pharmaceutical is what a company does and is commercially viable. Fourth is a company that actually exists. It's based near Purdue. They essentially evaluate tribological performance for wind turbine gear components. So these are not random examples or rather my wish list, but they're things that actually people are working on. And as a consequence of that, there is a wide array of future opportunities that will be available for a computational scientist in general, but a computational material scientist in particular, because I mentioned that because that's my secondary background. So as a computational scientist, you'd basically be an integral part of any multidisciplinary nanotechnology-related project, where you'll have to frequently collaborate with experimentalists, dabble with different computational techniques. You need to choose the computational techniques depending on the scope and the application, and also on what the length and time scale of the observed phenomena. You need to provide theoretical support to experimental observation, and also, depending on the company you work with or the project you're involved in, even enable direct application level predictions of material response. And to do this, that's a lot of it's a broad role that a computational scientist has that requires certain skill sets that you need not only get from academia. For instance, academia obviously does basic science better, and it molds the next generation of scientists. However, as George Cham mentioned, sketched in one of his comics from 2007, it's a very or at least the popular reputation is that it's very difficult for someone with advanced degrees with PhD to find relevant jobs in the job market. And training students for that is something that academia fails at. And essentially that's because there are not enough academic jobs to absorb all fresh PhD graduates, and academia does not prepare graduates for a life outside academia. And in many ways, as I mentioned a couple of times before, there's a risk of losing sight of the forest for the trees, where researchers get stuck in research comfort zones and not enough focus on application or solving current real world problem. However, not all is lost. If one plans ahead and recognizes the importance of a career course transition and develops the necessary transferable skills, there are skills sought after in industry that you can develop in academia based on different projects in the computational sciences. It could be machine learning, experience in data-driven approaches, multiscale modeling, an ability to evaluate the accuracy of a prediction, contextualize data in terms of whether that data has value or not, large-scale collaboration. All of these are skills that one can develop in academia and are valid in industry. So long story short, even though sometimes people paint a grim picture that if you go and do an advanced degree, it's difficult to find industry jobs. If one plans properly and develops the necessary transferable skills, there are transferable skills from academia that are useful in industry. And as again, George Sham sketched here, sharp analytical skills is one of it. And in jest, it's also the lower salary expectations. So in that context, if I move on to if one recognizes the need for transferable skills and develops that appropriately, what are the industry opportunities that would be present to a computational scientist after an advanced degree? So now, again, industry adoption of computational science and computational scientists is a relatively new, it's a relatively new phenomenon. And one of the earliest times I'd seen a big company actively using all the keywords in their public press release, such as rapid accurate prediction, quantitative properties prediction, fundamentally physics-based approach, data-driven methodologies, multiple simulation scales ranging from electronic to macroscopic properties. All these keywords that are relevant to computational scientists. One of the first time that I saw a big company mentioning that was in 2018. And a lot has changed in the world since, but the adoption of different companies in terms of leveraging computational science in their respective application has only grown more and more so. So in terms of that, the types of jobs that you can target, and if you look at these bullet points, if you go down in that list, that is essentially an increase in the level of qualification that you need. So the more down you go, then the need for a PhD becomes more and more. But in general, if you have a computational science background with some relevant domain knowledge, there are data science jobs that you can apply to. There are application scientist roles at big software vendors like Schrodinger, Amsterdam Modeling Studio, both of which are accessible even to a master's level student. But in the current scenario, this might change in the future, but to actually fully leverage the fundamental computational science domain knowledge, one needs to work on companies focused on integrated workflows. But currently, this would require doctoral level degrees. So an example of a company is the company that I work for, Avantgarde Material Simulation. There's another company called PeptiLogics where a colleague of mine works, a former colleague of mine works. They essentially dabble with protein docking simulations and multiscale simulations for drug discovery. Sentient Science is the other company that essentially does what I mentioned before. It's a company near Purdue which does multiscale simulations to design gears for wind turbines. So now there are lots of opportunities out there, starting from someone with a master's level degree with a sufficient broad background, all the way to a doctoral degree with sufficient depth in fundamental research. However, having all of those skills would be moot unless the research career is planned from an early level. So it's important to seek opportunities instead of jobs, an opportunity to expand your skill set. This is particularly important if you're pursuing the PhD route because, again, for the number of PhDs that are granted out in the world today, there are very few academic jobs that you can get. Which is why it's important to seek opportunities and collaboration that will continuously develop your transferable skills. And once that skills develop, at some point there'll be sufficient overlap between between available jobs. And of course, the right combination of skills can also provide an opportunity to be a job creator in future tech. And again, as a computational scientist, or specifically a computational material scientist, there is that opportunity to seamlessly transition across application industry domains because for breadth of domain knowledge that you get. However, there is a need to develop a central long-term goal if you want to cross-transition between academia and industry. And of course, as a consequence of that, it's important to plan, but plans have to be flexible. And with that, I'll essentially conclude the talk with stating computational sciences is of industry relevance. I showed some academic research that was done, moved on to some of the actually commercially viable computational workflows that exist, and with the future wish list of where this is going. And there are several companies looking to fund such work. However, going into the future and to avoid a hype cycle's trough of disillusionment, it's important that all the companies involved in this strive to make robust predictions and retain consumers' trust. And as a consequence, specialized computational workflows are important because specialized computational workflows that simplify decision making is what make any tool commercially viable. And transferable skills can be developed in academia, and there is industry in computational sciences looking for those transferable skills. However, one has to avoid the research silo and seek opportunities and collaboration. And with that, I would like to conclude the talk, and I'm open to questions.